Hello. So, in this video we are talking about rational functions and in particular the domains of rational functions. So, we want to know how do we figure out the domain, where are discontinuities, things like that. Okay? So, domains. Remember irrational functions, right? These are just some f of x over some g of x. Well, if we're talking about domains, then obviously we want to not be dividing by 0. It's usually not a good plan, right? So, first step, sort of an obvious but easy to overlook thing is that the bottom needs to not be 0. Fair enough. But on top of that, we also need to make sure that the f of x and g of x themselves also both work, right? They're also defined. So the domain, the sort of natural domain, is the largest set that works, meaning that everything is computable, everything is good for the top, f of x, the bottom, g of x, and the overall fraction, meaning that we don't want the bottom to be 0. Okay? So let's look at an example. Let's say we have r of x here, and we have that nice x squared plus 5x minus 6 over x squared plus 5x plus 6, right? Well, looking at this, right, we have our three things to check. The f of x, the top, the g of x, the bottom, and we don't want the bottom to be 0 bit. Okay, well, the top and bottom functions, they're both polynomials, so they work for any real number. So we have no restriction to worry about there, right? But we also want to make sure the bottom isn't 0. So we want to, in particular, we want this, right, x squared plus 5x plus 6 not equal to 0. Well, we can factor it, right? The top and bottom, we both factor. Note here that when I'm talking about domain, I'm not going to do any simplification. The domain bit to find the actual domain of the function is before any simplification happens. So even if I could cancel terms here, which, you know, in fairness, I can't, but even if I could cancel something like if it were x plus 3 over x plus 3 and be like, those cancel out, I don't want to do that when doing domains because the domain cares about the original form and not the simplified form, okay? So we want to take that bottom and be like, okay, x plus 2 times x plus 3, I want that to not be 0. Well, the only way that would be 0 is if x is negative 2 or x is negative 3. So those are the values I want to dodge, right? I want to say, okay, x is not negative 2, x is not negative 3, because if they were, I'd be dividing by 0, and, you know, everything would go horribly wrong. You go to math jail, et cetera, okay? So the total domain then, right, we had no restriction for the top or bottom because they were polynomials. All we had left was where the bottom was 0. So our overall domain is x can't be negative 2 and x can't be negative 3, which we could just list out like we have here. But we can also write it as this sort of interval notation, right? Negative infinity to negative 3, not including negative 3. Also negative 3 to negative 2, not including those endpoints. And negative 2 to infinity, again, not including endpoints. Also, we could do this with the set notation, right? Take all of R, right, all of the real numbers, set minus the set negative 2 and negative 3. So these are all ways that you sort of could see the domain commonly listed. All right, so polynomials are pretty much as nice as functions get. Let's look at a bit more of a worse situation to see when we want to care about that f and g part. So let's look at this example. So again, we want to know what is the domain of, in this case, h of x. Well, again, we want to look at the top and bottom and look at any domain restrictions there. So for the top, we know that because it's square root, right, an even root, we want the inside to be not negative. So we want to take the inside, that negative x plus 1, set it greater than or equal to 0, and that gives us that 1 is greater than or equal to x, or x is less than or equal to 1. Same deal with the bottom. So we take the bottom, we say, okay, again, square root, so we have an even root here. That means that we want the inside to be not negative, so we have x plus 1 greater than or equal to 0, and that gives us that x has to be greater than or equal to negative 1. And finally, so that was the top and the bottom, but we also want that the bottom is not 0, so we're not dividing by 0. So we take the bottom and we say, okay, we want that to not be 0, so then we can sort of try to isolate x, right? We move the 1 over, square both sides, subtract 1. This only happens when x is 0, so we have to avoid 0, right? So we have the restriction of the top, the restriction of the bottom, and x can't be 0, because if it were 0, that would make the bottom 0, and we'd be dividing by 0. All bad things. Okay, so how do we get the overall domain? Well, h of x's overall domain are all three of those pieces. X has to be less than or equal to 1, x has to be greater than or equal to negative 1, right from the bottom, and x can't be 0. But we can't just say this because that's sort of not obvious how this would work. It would be better if we could do this in some sort of interval notation, for example. And the best way to do that is by using a number line. So we basically want to plot each of these things on the number line sort of separately. So for example, the orange one, right, x less than or equal to 1, well, that would be a line starting at 1, including 1, and anything to the left, right, just for that part. The purple part, well, it has to be greater than or equal to -1, so we start at -1, including that, and anything to the right. And finally, for the bottom not being 0 part, we want to say, okay, 0 can't be in the set either, right? So we have the open hole at 0 because we're trying to avoid that. And now what we want is to take everywhere where all of that sort of overlaps. So you want to think about moving the top and bottom lines onto the number line and taking the overlapping part of that, which when we look at where they overlap is just that -1 to 1, but not 0, right? Because we pulled out 0. So that gives us that we want -1, including -1, to 0, not including 0, and 0, without including 0, up to 1, including 1, right? So we have the brackets on the outside and parentheses on the inside. Okay. All right, so what we do? Well, went through and talked about domains of rational functions and how really it's sort of one of those things that once you sort of think about it is not surprising, perhaps, where, right, we have a function at the top and a function at the bottom. Well, in order for anything to be computable, both of those have to be computable, right? So we need that any number we plug in works in the top and the bottom, so we have to worry about those domains. And we don't want to divide by 0, so we also need to know where's the bottom 0 so that we can basically avoid that when we try to compute the overall function. Okay? So that is that.